Good afternoon, everyone. I'm Hwasong Lee from NAVER Clova OCR team. In this talk, I will talk about the experience of developing deep learning OCR technology for Japanese language. For your information, NAVER OCR is being serviced as line-brain OCR in Japan. What is OCR? OCR is short for optical character recognition. It consists mostly of two steps. The first step is the text detection that locates text regions. The second step is text recognition, which is the job of recognizing the character string in each text region. Our team has a text detection publication in CBPR 2019 and the text recognition publication in ICCB 2019. When our team started research on OCR, we got a lot of questions like, isn't the OCR a conquered technology? What do you think? Do you agree with that question? I would say that's not true. Here is an example. In this image, you can see vertical Japanese text, rotated text, and very small text. What should look like the best detection result? Results for the most famous open source Tesseract are here. It tries to detect simple horizontal text, but it has failed because there are no simple horizontal text here. Our results for the same input image are here. Recent deep learning-based OCR can detect very small text, rotated text, vertical text, and multilingual text without any false positives. This is the agenda for today's presentation. The first, I will talk about things to know when applying recent OCR approaches to Japanese language. The second is the introduction of our text detector. The third is about our text recognizer. And the final is the explanation on our full pipelines for Clova OCR. Although OCR has improved a lot, there are many problems with applying it directly to Japanese language. Since deep learning technology began in 2012, there have been a lot of research using deep learning in the OCR area. The graph on the left is for text detection accuracy over year. As you can see, deep learning-based detectors have improved continuously and rapidly. The graph on the right is for the text recognition results. It shows the same trend as text detection. However, most papers deal primarily not with Japanese language, but with English language. Since OCR is a language-related technology, we should look carefully at the differences between Japanese language and English language. The first key difference is there is no space between words in Japanese language opposed to English language. The second key difference is there are many cases of using vertical writing. Even as in this example of newspaper, there are many cases that use both vertical and horizontal writing at the same time. The third key difference is the number of characters. English language requires only 26 characters, but Japanese language requires over 3,000 characters. With these three key differences in mind, let's move on to the next explanation. From now on, I will introduce the text detection for Japanese language. As I mentioned before, existing papers are based on word or line unit detection, which means that the existing detector does not allow space in a box. In order to handle a long sentence in Japanese language, we locate each character and combine them. That is our approach. Here are some factors that make it difficult to detect text. The first one is the extreme aspect ratio compared to general object detection. The second is shape distortion. Texts are usually printed on cloth or paper, in which case text suffer from distortion of shape. The third is variety of character sizes. These factors are caused by line or word level detection. How about character level detection? The extreme aspect ratio is no longer a problem, as each text region contains a single character. Shape distortion will be reduced in the case of a single character compared to word or line. The different character sizes is no longer a problem since characters are independently processed. Then what are the necessary annotations? Here's an example that we've done for character level ground truth. You can easily guess it costs a lot of money and time. Eventually, this made our team to focus on weekly supervised training. Pixel level annotation is very strong supervision for segmentation task. The weak supervision is an annotation for an object with a box, a point, or even a text. In summary, we would like to detect text area at character level without character level annotations. All right, we are ready to discuss the model of CRAFT. CRAFT is short for Character Region Awareness for Text Detection. There are two types of output in CRAFT. The first output is region score, which is considered to be the probability that the given pixel is the center of the character. The second output is affinity score, which is about the center probability of the space between adjacent character boxes. Let me give you an example. If this image is given as an input, region score must be like this scene map, which will be used to find individual character areas. Affinity score must be like this scene map, which will be used to locate line or word level areas along with region score. In order to train craft the model, the ground truth about region score and affinity score must be suggested. When annotations of character level are provided, 2D Gaussian distribution corresponding to each rectangular shape is the ground truth for region score. In order to generate ground truth for affinity score, the affinity box from adjacent two character boxes must be created. If you draw two diagonals in a box, you will see triangles above and below. The affinity box comes from the lines that cross the center points of the up and down triangles into adjacent character boxes. In this way, affinity boxes can be easily defined. The ground truth for affinity score can be produced with affinity boxes and corresponding 2D Gaussian distribution in the same way as generation of region score ground truth. As I mentioned before, we do not want to annotate character bounding boxes, but want to use word or line level annotations through weekly supervised training. The training process has two steps. The first step is to train the model with synthetic images. Since the annotation of character level can be given in synthetic images, the model is directly trained with synthetic data. The second step is to train the model with real images. To get character level annotation for real images, we crop text regions with word or line level annotations. If we inject the cropped images into the model estimates the region scores. After some computer vision techniques have been applied, bounding boxes for each character can be obtained. Then we can generate pseudo ground truth for real images. With the pseudo ground truth, the model is trained with character level annotations. This is the overview of generating pseudo ground truth. When word level annotations are given, we crop text regions and inject them to the network to get region score maps. Conducting watershed labeling and minimum bounding box operation gives annotation of the character box. This shows that character region scores changes as learning progresses. As learning progresses, prediction become more accurate. We can also see that the estimation of character box becomes more accurate too. All right, let's talk about the post-processing. The post-processing is very simple. For a given image, the region score map and the affinity score map are binarized so that the region of character and the region of affinity can be obtained. Then we just merge two binary maps and do labeling process with OpenCV function. Finally, after applying the minimum bounding box operation, we can get word level text region. As you can see, post-processing is very simple yet efficient. We use only 3 OpenCV functions here. I will give you some qualitative examples here. Craft estimates region score, affinity score, and does post-processing. For multilingual case, Craft estimates region score, affinity score, and does post-processing. Since Craft can locate well curved text areas, it is also possible to adjust curved text area to flat horizontal text regions. This is the movie clip for introduction of our method. Craft can rectify curved text for better recognition result. This is a result from detection frame by frame. Left is region score, the right is affinity score. In summary, using the proposed character level detection method, long sentences in horizontal or vertical writing can be localized. Even long curved text can be detected. So far, I talked about the text detection. From now on, I will explain the text recognition for Japanese language. As I mentioned earlier, the Japanese language requires a text recognizer that handles 100 times larger characters than English language. In order to address these barriers, we have studied a number of papers in the field of text recognition. What is syntax recognition? Syntax recognition is the task of recognizing character string in an image patch input. In this case, recognition should estimate character string of UNITED. There have been a lot of researches on STR. But when we looked into their evaluations, we found lots of problems. What are wrong with Str comparisons? This is a list of prior methods by year. Firstly, as you can see, the training data sets are inconsistent. Secondly, evaluation data sets are also inconsistent. There are many dashes here, and dash means not reported in the paper. And speed and memory are not always evaluated. Our solution to this problem is an unified STR evaluation. We have unified training data set and evaluation data set, and we have measured time and memory consumption for each method. Here we have 6 relevant papers, and each paper can be seen as a combination of 4 modules. 4 modules are transformation, feature extraction, sequence modeling, and prediction. But I will not cover the details of each module due to the limitation of presentation time. Hereafter, we treat model as a model combination. We evaluated each combination in terms of accuracy, inference time, and the number of parameters. These 6 combinations adopt 2 options for transformation modules and 3 to 2 options for the following modules, which means that these 6 combinations are a subset of all possible combinations. We consider all possible 24 combinations of STR modules. We plot the performances as plots accuracy versus time and accuracy versus memory. Speed is typo, I'm sorry. We first show the 6 prior module combinations on the accuracy versus time plot. And then on the accuracy versus memory plot. We then plot all possible combinations on the plot. These are the final trade-off plot. With these plots, we can choose the model according to certain performance requirements in terms of accuracy, inference time, and size of the model. One interesting observation is that the best accuracy model is not from existing combinations, but from newly explored combinations. Surprisingly, state-of-the-art performance is achieved by the best accuracy model. We have trained this model with the increased number of characters to handle Japanese language. With this model, Japanese characters can be recognized in a long horizontal or vertical sentence, even in a long curved text sentence. Okay, we are ready to move on to the explanation of the full pipelines for Clova OCR. For a given input image, text detection can locate each text area with the box and its orientation angles. Then each box is rotated to compensate for the rotation of the text. Each text region is injected into a text recognition model, regardless of each language and types of writing. Then we will get the results of recognition. This shows that our single recognition model can handle horizontal and vertical text in Japanese, Korean, and English language. All right, it's almost the end of my talk. Before leaving, I would like to share our web demo site. In the web demo, we provide the combination of text detection and text recognition. We currently use more advanced model compared to our paper model. The basics are the same. Thank you for listening.